I do need it.
So I've not taken the time to write out the lecture like I had done with you, which takes some effort. I wrote out some notes, so I don't have to write here by hand. Say this. Speak so long, because these would be motions so that you can refer back to this class. So I'll have to guess with trying to get the same thing. And nothing wrong with that.
You guys can't see that? You guys must need glasses.
I can read it.
Oh, there we go.
Read that?
Oh, yeah.
We were talking about the gas smoker, and
You
I
read this
mentioned
yesterday.
that these are typically instruments that measure the pressure versus temperature response to volume, and the volume at constant temperature, or the pressure volume product is proportional to temperature. And the temperature is equal to the limit of PV over R as the pressure goes to zero and the volume goes to infinity, either the motor volume. And recall the compressibility factor Z, which can be expanded in the imperial notation. Here's the expansion of volumes. We rewrite this, solve for this PV over R, then it's T times a function of volume. And you see as the pressure gets low, the volume gets big, this collapses to 1, the ideal gas state. So that's the way these thermometers are used. You have to measure this function versus how the pressure per volume, and extrapolate to infant dilution of the volume or zero pressure. And those are extraordinarily sensitive, very, very cumbersome to use. Hardly any about even has one. There's a few in the world. They're mainly at those laboratories that maintain standards for governments, but they're used to standardize other thermometers, secondary standards that we can buy in our laboratories and take temperature measurements with fair confidence that they're reasonably accurate. A practical thermometer, the workhorse type for science and engineering, one practical thermometer is the resistance thermometer. The electrical resistance of a conductor, a piece of wire, or whatever, has a temperature dependence, and it's characteristic of the material. And if you know that resistivity for a particular element you're using, you can measure the resistance accurately in some bridge network, and thereby infer the temperature. Platinum is the element of choice. Why? Because it's incredibly stable. It's just stable over time. You can buy these as 100-ohm thermometers, come in other varieties as well. That's the most common. I have one. I haven't had one here. Just out of some instrumentation that I've been working on. There's not much to look at. Here are a couple of heaters that heat a small object, and they're shoved into little holes in the object outside my thumb. And here's the monitor, the platinum resistance monitor, shoved in there, measuring the temperature. Of course, that's part of the feedback that the controller is used to maintain the temperature. So that's a pretty cheap $1 or so. But in the laboratory, we're not really doing trouble work, your benchmark work, then we use much sturdier and more impressive looking platinum thermometers. But that's something that all you engineers need to know about, and you chemists are going to be experimentists need to know about. The resistance of platinum follows this calendar equation, calendar Van Dusen equation. And it has A, B, C, 3 parameters in it, which means that it had to be calibrated at 4 different temperatures. And those are 0 degrees centigrade, 100 degrees centigrade. The boiling point of zinc, which is 419.53, and the boiling point of liquid oxygen, which is minus 182.96, and those are highly reproducible temperatures. So that's used to standardize, that's used in places like NIST and other laboratories to standardize the platinum resistivity, and platinum that's sufficiently pure follows this quite nicely over wide ranges of temperature, and they're very, very useful. Now, we're going to talk about temperature measurements or inferences from black body radiation. And I just have to assume that you're familiar with black body radiation from perhaps other chemistry courses or perhaps your physics studies. How many of you are familiar with black body radiation and what it is? 2, 3, 5. Okay. Well, I can't give you a full lecture on which because it's a hell of a lot more interesting than we're talking about. But here goes. A black body is any object that absorbs all the light that falls on it. If you shine light or give it your black. But if it's in equilibrium with its environment, then it has to, it's receiving radiation from its environment, it has to radiate back so that the incoming energy from radiation bounces the outgoing at equilibrium. And so it has to radiate as well. So it absorbs and emits radiation at equal rates. And we say the emissivity of the black body is 1, or the absorbance of it is 1. And one source of black body radiation for spectroscopic study does an isothermal enclosure. How many of you ever heard of an isothermal enclosure? Anybody? Okay. Basically, it's a cavity, any size. I mean, here's how to, any material. I mean, here's what material. I mean, anything you can build a cavity, build around the cavity. Inside it, there is radiation, always radiation. And we know that because we learned back when we were talking KMT that the walls of solids involve atoms that are vibrating, oscillating, moving around. And J. Kirk Maxwell developed his theory of electromagnetic radiation based on the experimental work of guys like Michael Faraday, who discovered electromagnetic induction. If you accelerate a charge up and down, then by God, it radiates light. If you do it at a fast frequency, it radiates light at a high frequency. If you do it at a slow frequency, it radiates light at a slow frequency. High frequency, short wave, low frequency, long wavelength. Radiates at the speed of light, it's pretty fast. Now that's the world we live in, and we're counting on that to work. We all have our cell phones. For example, how do these talk to those towers? They talk on radiation. And in those towers, if they're sending us a message, they oscillate electrons up and down at pattern frequencies. It sends out light at pattern frequencies. It goes across an antenna in our cell phone and excites sympathetic vibrations of the electrons in there. They can amplify and turn it into the picture of your dog, your dog, whatever the important stuff's coming. So there's always light inside the cat. You can't see that just because our eyes are very feeble to see the light. We see itty teensy of the spectrum of light, from way out radio waves and longer to gamma rays that short. You just see a little bit. So whether we can see it or not depends on its temperature. I certainly close. So here's a picture of one. Not very good. Look, it's a cavity in a lump of something, and it's raised to a temperature. It's in a heat bath or in an oven or whatever, so it comes all up to the temperature, and it's still full of light. Now you say, well, does every bit of light that falls on this surface here absorb? Well, it might just reflect off. But even if it does reflect off, often it will be absorbed because it's trapped in there. So it satisfies the criteria of black body. Now, if we just had a way to go in there and look at that light and sample it, we'd know what the spectrum of black body radiation looked like. Well, put a little hole in there, and then some of it leaks out. And you put an analyzer, and you get a spectrum. And the part we can see would just be any that's in the red to violet range. We don't see the infrared up here. We don't see the UV below. So the studies initially were made with light that we can see in the visible spectrum, principally. So the walls, they need to absorb that energy. The cavities fill with light. The density of the light is proportional to the density of the energy in the light is proportional to the Fourth cloud temperature. That studied physics, heard of the Stefan Boltzmann law. That's it. That constant's well known. That constant proportionality is well known. So we know a lot about black body radiation. Here are the characteristics of a typical spectrum. If you look at the intensity versus the wavelength, the intensity falls off to zero at very, very short wavelengths for very high frequencies, rises to a maximum, then tapers off. Well, that looks sort of familiar, doesn't it? Looks almost like a Maxwell Boltzmann distribution speeds. They're similar, but it's a different function. It has some commonality. This pattern follows Planck's law of black body radiation, one of the most important milestones in the development of physical science. The year was 1900. I told you about the equipotential theorem and about how it failed. We used it only in situations where it didn't fail. But that was pushed far enough, it failed, and it failed big time when you were looking at this black body radiation. The equipotential theorem said that this curve should just go on up forever. Instead, try to go to zero. And that drove people crazy. Max Planck figured out an explanation for it in 1900. That day he did that was the moment that quantum mechanics was born. Fundamental quantum mechanics known to any living being we're aware of prior to that.
That -1, is that to in the power?
Beg pardon?
The -1, is
Yeah.
that in the power?
No, it's yeah. So, now here's that law. C is the speed of light, H is Planck's constant, a universal fundamental constant, one of the really significant constants, right up there, the Newton's gravitational constant. Note that this E over HC lambda KT looks suspiciously like the Boltzmann constant, but it is one, not. What's a Boltzmann constant? E to the minus of energy over KT or R, right? That's the Boltzmann constant. This is E to the plus something over something. Has the temperature in it, has KT in the denominator right place. Not quite there, but it can be transformed so it, the beauty of the Boltzmann constant here, by converting that law from wavelength